This video is an introduction to the types of organic compounds and organic functional groups, and there are a lot of them, but this is just an introduction. So what is an organic functional group? Well, it's not a complete compound, but rather it is part of an organic compound, often a reactive site in a compound. For example, CH3 something is part of many organic compounds, including a small molecule such as methane here, and including large molecules like N-hectane, carbon 100, hydrogen 2O2. And in this formula, methyl group is part of that compound. Now, students of organic chemistry, you must memorize a variety of organic functional groups and the types of organic compounds that they form. So let's get started. Alkyl groups. We've just mentioned the methyl group CH3 something, as for example in the compound methyl chloride. Now if we have a methylene group, it's a CH2 group, but that means there's two more single bonds to something, as for example in the compound methylene chloride. And here's a structure of it, CH2, CCl2. Chlorine is known to be a pale green gas, and in these models, chlorine is represented by green atoms. Two carbon alkyls. An ethyl group would be the simplest, CH3, CH2 something, as for example in the compound ethyl chloride. Now, we can also have an ethylene group, which has two methylene groups, and each one has a single bond to some substituent, as for example in the compound ethylene chloride. Here's CH2Cl, CH2Cl, ethylene chloride. A few more alkyl groups. Let's look at 3 carbon alkyls. Well, straight chain alkyl N-propyl group, as for example in N-propyl chloride is CH3, CH2, CH2Cl. Well, it turns out that there is another isomer of the propyl group called an isopropyl group, in which case the substituent is on the second carbon or the middle carbon, as for example in the compound isopropyl chloride. So we have CH3, CHCl, CH3. Now, whereas there were 2 different isomers of the propyl group, there are in fact 4 different butyl isomers, and I've drawn 4 butyl chlorides below to illustrate this. We'll start with N-butyl chloride, N meaning normal or unbranched or straight chain, as shown with the chlorine on the end. This next structure is named isobutyl chloride. Now, it's butyl because there's 4 carbons, but why iso? Well, in the nomenclature of the common system, and there isn't much, but there are a few rules, iso defines that a compound has a methyl group on the second last carbon from the end of the chain. Well, what's the beginning of the chain? Well, the longest chain that contains the functional group is the main chain. The head carbon is defined as the carbon bonded to the substituent, so this marks the beginning of the chain. Here's the end of the chain. Second from the end is a methyl group, and that defines the iso group, isobutyl chloride. There is also an isomer called sec-butyl chloride, short from the term secondary butyl chloride, and sometimes abbreviated S-butyl chloride. Notice in the structure that one of the internal carbons has a substituent on it. Now, because this head carbon is bonded to 2 other carbons, it's defined as being a secondary carbon, and the name sec-butyl chloride derives from that. The 4th and final butyl isomer is named tert-butyl chloride. If you look at the structure, the head carbon is bonded to 3 other carbons, and so that defines what's called a tertiary carbon. So the name can be tertiary butyl chloride, sometimes written T-butyl chloride or even T-butyl chloride. Let's look at a couple of alkenyl groups taken from alkenes. CH2 double bond CH something is called a vinyl group. An example would be vinyl chloride. And here's the structure of vinyl chloride, CH2 double bond CHCl. Now vinyl chloride is a monomer that is polymerized to polyvinyl chloride, a plastic often referred to simply as vinyl. So rubber boots, raincoats, shower curtains, and even vinyl siding on a home is generally polyvinyl chloride. This next compound, CH2 double bond carbon with two substituents, is referred to as a vinylidene group. An example would be vinylidene chloride, CH2 double bond CCl2, and there's the structure of vinylidene chloride. Another group that is similar but different than the vinyl group is called an allyl group. Some people call it an allele group. CH2 double bond CH, CH2Cl is an example of allyl chloride. So what's the difference between allyl chloride and vinyl chloride? Well, allele means that there is a substituent on a carbon next to a doubly bonded carbon, whereas vinyl means that there's a substituent directly on the doubly bonded carbon. Let's then look at some types of organic compounds. We'll start with the simplest. Now in these compounds, R, the letter R, represents any alkyl group or sometimes simply the rest of the molecule. An alkane is a saturated hydrocarbon. It's also referred to as a paraffin. Think of paraffin wax as a good example. Another simple example is propane, and here's its structure, CH3, CH2, CH3. All carbons are saturated with hydrogen. Alkenes have one or more carbon-to-carbon double bonds. An alternate name for an alkene is an olefin, which means attracted to few things or attracted by few things. And if you've smelled alkenes, you know why few people are attracted to them. Simple example is propene, CH3, CH double bond, CH2. Keep in mind always that carbon has 4 bonds. A hydrocarbon with one or more carbon-to-carbon triple bonds is referred to as an alkyne. Simple example is propine, and there's its structure, CH3, C triple bond, CH. RX, where X is a halogen, fluorine, chlorine, bromine, or iodine, is referred to as an alkyl halide, occasionally called a haloalkane. There's N-propyl chloride is an example of a simple alkyl halide, CH3, CH2, CH2Cl. Aromatics, sometimes called arenes, are compounds derived from benzene, C6H6. Now, benzene is represented by all of the structures that are shown below. In this structure on the left, all carbons and hydrogens are shown. Other models are skeletal structures, and it's understood that there's a carbon at the end of every line or at the junction of any two lines. Hydrogens are not shown in these structures. So benzene is a 6-membered hexagonal carbon ring. It has an alternating pattern of single and double carbon-to-carbon bonds. Now in reality, all 6 carbons share the 6 pi electrons. There are 3 pi bonds, 2 pi electrons per bond, total of 6 pi electrons. But they are not localized as the structure would indicate. Rather than having 3 single bonds and 3 double bonds, benzene actually has 6 bonds, which might be described as being 1.5 bonds. And these two illustrations on the right serve to show this, that the 6 electrons, the pi electrons, are shared equally among the 6 carbons. Here we have a phenyl group, C6H5 something. That is referred to as an aryl group, sometimes abbreviated AR when bonded. Now the benzyl group, C6H5CH2, is also shown here, and it's often confused with the phenyl group. They differ by this methylene group, so try and keep them separate. Chlorobenzene, C6H5Cl, put a chlorine on here, and benzyl chloride, C6H5CH2Cl, put a chloride on here, are examples of aromatic compounds. Ethers have an oxygen atom that is singly bonded to two alkyl groups, as illustrated in this structure. Now the oxygen's bonding in an ether is very similar to an oxygen's bonding in water. And so the basicity of an ether, pKb about 17, is similar to that of the basicity of water. It's the same oxygen donating the same-ish pair of electrons. However, the acidity of an ether is quite different. Ethers are completely non-acidic. Ethers do not have the hydroxyl hydrogen to donate, and as a result of that, you'll sometimes see ethers used as solvents in reactions where you're using a very strong base, which would otherwise deprotonate other solvents like alcohols, which have hydroxyl hydrogens. Diethyl ether, ethyl oxygen ether, is a common organic solvent. CH3, CH2O, CH2, CH3. So oxygens are depicted red in these models. Diethyl ether is nonpolar. Its dielectric constant is only 4. It has a low boiling point, 35 degrees C, and that makes it a good solvent, general purpose solvent in the organic laboratory. So you can use ethers to extract organics out of water. The ether will separate from water in a separatory funnel. Being less dense, it's the upper layer. You can then separate them. The two layers, take the ether layer, dry it, and then evaporate off the ether relatively quickly. The boiling point is 35, and recover your product. Organic peroxides. Now, peroxides contain the oxygen to oxygen single bond group. There are two kinds. We have dialkyl peroxides, ROOR, and hydroperoxides, ROOH. Here's an example, dimethyl peroxide, and here's a hydroperoxide, T-butyl hydroperoxide. Both of these are analogous to hydrogen peroxide. The peroxide bond is weak, only about 50 kilocals per mole. That makes it reactive and unstable. Especially when you think of the strength of an oxygen to carbon bond or an oxygen to hydrogen bond, typically in the range of 90 to 100 kilocals per mole. So a lot of heat can be released when an oxygen to oxygen peroxide bond is broken and an oxygen to carbon or oxygen to hydrogen bond is formed instead. Now peroxides cleave homolytically, producing two free radical groups. So here is the peroxide bond cleaving homolytically, meaning breaking evenly. Notice one electron going in each direction. These fish hooks, these half arrowheads, indicate the transfer of one electron, producing in this case an alkoxy free radical. There's the free radical, the unpaired electron, and a hydroxy free radical. Alcohols, ROH, are similar to water, not only in their structure, but also in their acid-base chemistry. Water is a very weak acid. Its pKa is 15.74. It's also a very weak base, pKb 15.74. Likewise, alcohols are very weak acids, pKa approximately 16, and very weak bases, pKb approximately 16 as well. Ethanol, and there's the structure of it, CH3, CH2, OH, is the alcohol of beverages. Aqueous solutions of isopropyl alcohol, here it is, CH3, CHOH, CH3. Here again we see this isopropyl group. 30 to 70% aqueous solutions of isopropyl alcohol are sold in pharmacies under the name rubbing alcohol. Don't think that the uncharged hydroxyl group of an alcohol, for example here, is even remotely close to the hydroxide group, OH minus, of the hydroxide ion. See, whereas the hydroxyl groups of water and of alcohol are neutral, the hydroxide group in sodium hydroxide is a strong base, pKb negative 1.74. This is a good electron donor. Negative charge makes a huge difference. Next, we're going to look at phenols. Now, this compound, C6H5OH, is a specific compound called phenol. But phenols are actually a class of compounds that are derived from phenol. Here's an example of a phenol, a phenolic compound. Common name is paracresol. And paracresol, Wikipedia tells me, is the major component of pig odor, present in human perspiration and believed to be the component of human odor that is attractive to female mosquitoes. Now, if you look at the structure of an alcohol and a phenol, they look alike, but chemically they're different. Alcohols are weak acids. They have a pKa of about 16, but phenols are actually mildly acidic. Their pKa is approximately 10. That's a large difference. pK values are powers of 10. We're saying that a phenol is 10 to the 6th or 1,000,000 times more acidic than an alcohol. And so, whereas alcohols will not react with sodium hydroxide, a phenol will react with it, neutralize it, if you will, acting as an acid, and dissolve in strong bases like sodium hydroxide. Here's an example of that chemical reaction. Sodium hydroxide, the hydroxide ion has a pKb of negative 1.74. Phenol itself has a pKa of 9.9. Our base is the electron pair donor, donating a pair of electrons to form a bond with the acidic hydrogen in phenol. Hydrogen is monovalent. It can't have two bonds at the same time. If it's going to form a bond to oxygen, then it has to break the bond that it currently has with phenol. That liberates water and gives us the conjugate base, sodium phenoxide. Now, the phenoxide ion is another functional group. Its pKb is 4. It's a moderately strong base. Since we're talking about acids, let's look at the most common organic acids called carboxylic acids, R-carbonyl OH. Now, the hydroxyl group in a carboxylic acid is acidic because it is bonded to the carbonyl group. See, carbonyl groups are electron withdrawing, and it changes the game. We don't have carbonyl groups in water or in alcohols, and those hydroxyl groups are not acidic, but in a carboxylic acid, in fact, it is acidic. Typically, they have a pKa of approximately 5. This is a structure of acetic acid, CH3, carbonyl OH. It has a pKa of 4.7, and it will react completely with strong bases like sodium hydroxide, producing the acetate ion, which is an example of a carboxylate ion. Here's the acetate ion, CH3, carbonyl O-, without its hydrogen ion. Do you recall the general acid-base mechanism? Here's our base, electron pair donor. Here's our acid, electron pair acceptor. The base will donate a pair of electrons to the hydrogen ion, the hydrogen in the acid. Hydrogen is monovalent. It can't have two bonds at the same time, so it has to break a bond with A. And so the base becomes BH, the conjugate acid of the base. At the same time, HA becomes A-, the conjugate base of this acid. So let's try that on a specific example. Here's a carboxylic acid, and here's the hydroxide ion. Carboxylic acids in general have a pK of approximately 5. Hydroxide ion negative 1.74. What's the mechanism going to look like? The base will donate a pair of electrons. Any one of these three pairs is identical to the hydrogen, the acidic hydrogen in the carboxylic acid. Hydrogen is monovalent. It can only form one bond at a time. So that means it has to break this bond to the carboxylic oxygen in order to form a bond to the hydroxide. Water is the product and a carboxylate ion. Now, the pKb of the carboxylate ion is 14 minus the pKa. 14 minus 5 is 9. And so this is basic enough that we can reverse the reaction by reacting with a strong acid, such as the hydronium ion, pKa negative 1.74. Notice that the pKa of the hydronium ion is equal in magnitude to the pKb of the hydroxide ion. Not surprising, since the pKa and the pKb of water is the same, 15.74. In any case, here's the reaction mechanism. Our base donates a pair of electrons to the acidic hydrogen. Hydrogen is monovalent. It has to break a bond with the hydronium ion to form the bond with the carboxylate. So water is produced and the carboxylic acid is reformed. Acid anhydrides are just what their name implies, acids without water. There's a structure of an acid anhydride, R carbonyl, O carbonyl R. Now in anhydrides, the R groups, R1 and R2, they can be the same or different alkyl groups. How do you form an anhydride? Vigorous heating will dehydrate a carboxylic acid. If you take a look at the reaction here, a total of one water molecule is removed for every 2 molecules of the acid. So here I have 2 molecules of acetic acid. It's heated up. Water is eliminated to produce the anhydride, in this case acetic anhydride because it's formed from acetic acid. And here is the structure of acetic anhydride, CH3, carbonyl, O carbonyl, CH3. Acetic anhydride is probably the simplest and most common acid anhydride used in the lab. This reaction, you may have noticed, is reversible. When you take an anhydride and heat it with water, then the water molecule will add, forming 2 carboxylic acids. Acid anhydrides are very reactive organic electrophiles, meaning electron acceptors. They are therefore often used in organic synthesis reactions. Esters are next. An ester is R carbonyl OR. Now their structure looks similar to a carboxylic acid, except we have an R group instead of a hydrogen. Now the R groups, the 2 R groups in an ester can be the same or different. Esters, in fact, are often synthesized by reacting a carboxylic acid with an alcohol in the presence of an acid catalyst. That's called the Fischer esterification reaction. Here's an example. Methylbutanoate, the flavor of apples, forms when butanoic acid reacts with methyl alcohol. Here's the reaction. CH3, CH2 taken twice, carbonyl OH, that's butanoic acid, reacting with methanol in the presence of acid, and a hydrogen ion catalyst will condense out water. Now notice it's not an acid-base reaction because the acid is not losing a hydrogen ion. In fact, the acid is losing the hydroxyl group, and it's the alcohol that's losing the hydrogen ion. So it really isn't any sort of an acid-base reaction. Condensation occurs when we get the methyl ester butanoic acid, methyl butanoate. Now the reaction yield is typically about 50%, more with small acids and alcohols, and it's a little bit less with large acids and alcohols. And it's also reversible. You may have noticed if I add water to the system rather than boil it out, heat it, and add an acid catalyst, the reaction goes in the reverse, forming the carboxylic acid and the alcohol. This is simply Le Chatelier's principle at work. Next group is an acyl group, R carbonyl something. The acyl group, like the carbonyl group, is an incomplete compound. That is, it's part of several classes of organic compounds, such as the acid halide, also known as the acyl halide. Now, acid halides, they're one of the most reactive electrophiles, electron acceptors in organic chemistry, and they're used to carry out very quickly a lot of organic reaction syntheses that otherwise would require long reaction periods. Now, the X in the acid halide represents any halogen. However, in practice, the halogen is usually not part of the reaction product, and so the least expensive acid halide, that it would be the acid chloride, is almost always used. And here's the structure of an acid chloride, R-carbonyl-Cl. Acetyl chloride, CH3, carbonyl-Cl, acetyl chloride, and benzoyl chloride, C6H5, COCl, are two common acyl halides. The formyl group, also known as the methanoyl group, is again part of other compounds, H-carbonyl something. And one of the groups we're going to look at next that the formyl group is part of is our aldehydes. And aldehydes have an R group attached to the formyl group, so it's R-carbonyl H. Aldehydes are flavorings and they are fragrances. Here's an example, propion aldehyde, a 3-carbon aldehyde, CH3, CH2, carbonyl H, has a fruity flavor. Benzaldehyde, C6H5, carbonyl H, has an overpowering cherry odor. Now, this particular aldehyde, formaldehyde, is a bit of an exception to the structure rule. It has one carbon, but it has two hydrogens and no R group. It's the simplest possible aldehyde. It's the only aldehyde that doesn't have an alkyl group attached to it. So formaldehyde was formerly used to preserve biological specimens, but it's been largely replaced since being designated a known carcinogen. Ketones are next. Ketones have the structure R-carbonyl R, similar to aldehyde, except two alkyl groups instead of one. Several ketones are produced by the human liver from fatty acids during periods of low food intake, aka fasting, or from carbohydrate-restricted diets. And I have here the structure and a model of acetone. Dimethyl ketone, commonly called acetone, is important. It's miscible in water, dissolves many organic compounds as well, and it's a good general purpose solvent, particularly because of its high volatility. Its boiling point is only 50 degrees Celsius, and so glassware rinsed with acetone dries quickly. Well, let's look at some organic bases, and alkylamines are certainly the most common organic base, and they're very similar to ammonia. An alkylamine simply has one or more of its hydrogens replaced by alkyl groups. Here is a primary amine. It has one alkyl group replacing a hydrogen, or we could say there is one carbon bonded to the central nitrogen. A secondary amine has two carbon groups bonded to nitrogen. A tertiary amine has three alkyl groups bonded to nitrogen. This last structure actually has four alkyl groups bonded to nitrogen, such that the nitrogen is no longer neutral. It's a nitronium cation, and this group as a whole is called a quaternary aminium cation. And so primary, secondary, tertiary, and quaternary alkylamines respectively have 1, 2, 3, or 4 alkyl groups attached to nitrogen. And when I say quaternary alkylamines, I do it in the spirit in which it's commonly used, but we understand that it's not truly an amine any longer. It's an aminium cation once it's quaternary. Now ammonia is moderately basic. Its pKb is 4.8, and so are the neutral amines. In fact, they're slightly more basic, typically about pKb 4. The quaternary aminium cation will be acidic, much like ammonium ion is acidic, and in fact, its pKa is approximately 10. So let's look at an acid-base neutralization reaction. We're going to use methylamine as our base. Its pKb is 3.4, and we'll react it with hydronium ion, whose pKa is negative 1.74. Now the base is the amine. It's got the non-bonded pair of electrons, which it can donate to any one of the three acidic hydrogens in hydronium ion. Hydrogen is monoprotic. If it's going to form a bond with nitrogen, it's going to have to break its bond to oxygen. That will produce the methylaminium cation, and byproduct is water. Now the methylaminium cation is the conjugate acid of the amine. We can calculate its pKa. It's 14 minus the pKb of the conjugate base, so 14 minus 3.4 is 10.6. We can reverse this reaction by reacting with hydroxide ion, pKb negative 1.74, a strong base. Any one of its three non-bonded pairs of electrons can form a bond with one of the acidic hydrogens. If hydrogen is going to form a bond with oxygen, it has to break its bond to nitrogen because hydrogen is always monovalent. The product will be methylamine and byproduct water. Arylamines, they're like alkylamines. There's an amino group bonded to an aromatic ring. So here we have a primary aryalamine with one aryl group bonded to nitrogen. A secondary aryalamine has two aryl groups bonded to nitrogen. A tertiary aryalamine has three aryl groups bonded to nitrogen. And when we have four aryl groups bonded to nitrogen, this would be a quaternary arylaminium cation. So, analogous to alkylamines, aryalamines have can be primary, secondary, tertiary, or quaternary when they have 1, 2, 3, or 4 aryl groups attached to nitrogen. This is aniline, C6H5NH2. It's a common aryalamine. Now, aryalamines are much weaker bases than alkylamines, and that's why they're presented separately here. Aniline, for example, has a pKb of 9.3, and this is because the nitrogens, the non-bonded electrons on the nitrogen, are tied up in the aromatic ring. Let me show it here. These pair of electrons are tied up in the aromatic ring, and they're less available for donation to an acid, making an aryalamine much less basic than an alkylamine. Aniline, however, is basic enough that it will react with a strong acid like hydronium ion. And let's show the mechanism for that. Aniline with a pKb of 9.3 and hydronium ion with a pKa of negative 1.74 will react completely. Nitrogen's non-bonded pair of electrons is the base. It's going to donate the pair of electrons to any one of the three acidic hydrogens in hydronium. If hydrogen is going to form a bond with nitrogen, it has to break its bond with oxygen because hydrogen is monovalent. And so as nitrogen forms a bond, forming the aniline chloride cation, at the same time hydronium ion is converted to water. Now the pKa of the aniline chloride cation is 14 minus the pKb of its conjugate base. 14 minus 9.3 is 4.7. And so this reaction could be reversed as well using a strong base. Let's look next at amides. R-carbonyl NH2. Now amides contain both an amino group and a carbonyl group. A primary amide has one carbon group attached to nitrogen. A secondary amide has two carbon groups bonded to nitrogen. And a tertiary amide has three carbon groups bonded to nitrogen. So primary, secondary, and tertiary amides have 1, 2, or 3 carbon groups bonded to nitrogen respectively. Despite their similarity to amines in name and appearance, amides are not basic. Instead, they are similar to alcohols, being neither basic nor acidic. You see, the non-bonded nitrogen electrons that are basic in amines are tied up by the adjacent electronegative carbonyl group, and so they're less available to be donated to acids. Amides, therefore, are quite neutral. They are relatively stable and unreactive compounds. Amides are pervasive in nature and technology as structural materials. For example, nylon plastics, Kevlar, protein, hair, spider silk, to name a few, are long-chain polyamides. Here is the structure of acetamide, CH3, carbonyl, NH2. Because of its low molecular weight, it's a low-melting solid used as a plasticizer and a solubilizer. It increases the solubility of many other chemicals. Nitriles. Nitriles have the structure RC triple bond N. Now, the prefix cyano is often used interchangeably with the term nitrile in industry. Inorganic compounds that contain the same group, C triple bond N, are called cyanides. For example, here's hydrogen cyanide. Potassium cyanide would be another example. Nitriles are relatively stable, unreactive compounds and pH neutral. Nitriles are found in many useful compounds, including cyanoacrylates, the superglues, and nitrile rubber gloves that are used often in latex-free laboratories. Here is a commercially important nitrile, acrylonitrile, CH2, double bond CH, C triple bond N. This monomer is polymerized to make polyacrylonitrile fiber, which is used in the manufacture of clothing under the trade names acrylic and Orlon. Nitro compounds contain the NO2 group bonded to an alkyl group. Inorganic salts that contain the same group are termed nitrates. Many nitro compounds and nitrates are in fact made from nitric acid. Now you want to notice that in both nitrates and in the organic nitro compound, the NO2 group contains the negatively charged oxygen and a positively charged nitronium cation, while the whole time the NO2 group is overall neutral. You probably are aware that highly nitrated compounds are very explosive, and I have two structures to show here of such. This is trinitrotoluene on the right, 3 nitro groups on a toluene ring, aka dynamite, and here's nitroglycerin. And that's probably enough for an introduction to organic functional groups.